I'm Dr. Debra Emmons. I'm the Vice President and Chief Technology Officer at the Aerospace Corporation, where we are solving the hardest problems in space. So a little bit about me. In that role, I manage our $60 million plus R&D portfolio and set our technology, strategies, and priorities. Also manage our experimental prototypes, our Commercial Space Futures Office, and our Solution Accelerator. So very much around the innovation pipeline, and this is, of course, what we're going to be talking a lot about today with our panelists. So I want to thank you all for joining me on this panel discussion. It is mission requirements driving space R&D needs. Certainly the pace and complexity of today's space missions is really driving us to see innovation and more investment there in our research. This is really going to be a panel that gives you the opportunity here to hear from leaders in industry and government addressing the space community's needs and challenges. And we're going to include topics today to delve into that include space as a critical infrastructure, advanced propulsion systems, and space exploration technologies. I am joined here on the stage here with a couple of our panelists, and then there's one in Zoom land, and I will introduce you to our esteemed panelists. We no longer have one of our panelists from Johns Hopkins, but we certainly have a representation here from industry and government, and then of course myself representing FFRDC. So let's introduce you here to our panelists, and then I want to also let you know a little bit about the format. So we'll get to know our panelists, and then we're going to go right into sort of the deep dive into, the topics that I mentioned, the space as a critical infrastructure, and then space technologies and the like. And then we'll have the conversations here, and then we'll have an opportunity to hear from you all. So you should submit questions as we go, and we will, take some of those as we go, and then we'll set some time aside at the end to be able to talk through any more questions that emerge as you hear from each of the panelists. And then we'll kind of have a close and do a little bit of a lightning round. All right, so let's introduce you here to our panelists. We're first joined here by Donnelly, Chief Engineer for Ignite and Product Centers at Lockheed Martin. With nearly 2 decades of experience, Diana has led cutting-edge programs and teams focused on transitioning innovative technologies to production while shaping Lockheed Martin's product and technology strategies. So welcome to Diana. On the Zoom line, we have Dr. Bryan Dorland, Principal Director for Space Technology in the Office of the Assistant Secretary of Defense for Critical Technologies. Dr. Dorland serves as the DoD's CTO for Space Capabilities, and he works across defense and intelligence and international partnerships to advance mission-critical space technologies. Welcome, Dr. Dorland. And then we have Kristin Houston, President of the Space Propulsion and Power System Sector at L3Harris. Kristin oversees propulsion and power systems that enable launch and in-space operations. She brings a wealth of experience from leadership roles in defense, aerospace, and commercial technology programs. So again, welcome to all of you, and glad to set the stage, and let's get right to talking about space as a critical infrastructure. So we've seen certainly in the news the topic of relegating, if you will, space as a critical infrastructure has been one that's had some debate. But what doesn't get debate certainly is that space is one of the fastest growing markets of the global economy. There are estimates here that space will grow by a factor of 3 by 2030, 1.4 trillion are some of the numbers here. And certainly, space systems are essential for so much of what we do. So whether they're formally designated as a sector of critical infrastructure, which they have been by the CISA, the Cybersecurity and Infrastructure Security Agency, we know that they are, that space serves as a key enabler, as the backbone to modern society, basically key for global comms and banking, navigation, defense, climate monitoring. I can go on and on. And certainly, we know that consequences could be dire or would be dire if there was a disruption to any of that. So I want to start here and talk a little bit to ask some questions here of the panelists about space as a critical infrastructure. And so I'm going to start with our government perspective, Dr. Dorland. So from the perspective of the DoD, how do you see the designation of space as a critical infrastructure influencing the national security policy? And then maybe adding on to that, what are the most significant threats, and how do you see the DoD working to address them?
All right, well, good afternoon. Can you hear me, Deborah?
Mm-hmm.
Okay.
Yes.
Good afternoon from Washington, D.C., where the snow is in the air and the planes are not. So unfortunate that I couldn't get down there, but it's great to be able to participate via Zoom. So I think just to emphasize some of the things you've said, I think what the government sees now, and specifically the Department of Defense, is we understand how important space is to our entire nation. It's not just about the Department of Defense. Space is increasingly true infrastructure to pretty much everything we do, and in a lot of ways, we lose sight of the fact because we just, for example, with GPS, which of course began as a defense program, GPS has become infused into the entire nation in terms of financial issues, commercial activities, even driving your car from one place to another. So we understand that that space has become critical to the nation and the world for more than just defense purposes. And we look forward. Looking to the future. The anticipation is it'll become even increasingly more fundamental to how we operate. So, given that, our primary responsibility to the nation as the Department of Defense is to ensure that that we have the ability to protect our critical assets, and those include both defense assets, but they also include commercial interests. They include those of our allies, and so forth. So, just looking ahead, you mentioned threats. When we look out ahead, we see a number of areas where there are some concerns. And as the CTO, as the Chief Technology Officer for the Department of Defense for Space, it is my responsibility and our team's responsibility to ensure that we understand what we think other nations are doing, and from a technology perspective, how we can maintain and in fact enhance the technological advantage that we have. So some of the threats that concern us now moving forward are we see among some nations, we see an increasing deployment, not just experimentation, but deployment of systems that potentially threaten our defense systems in space, intelligence systems, commercial systems, and those of our allies as well. Some of the key things that we're seeing now involve direct descent ASAT weapons. They involve directed energy weapons. They involve co-orbital weapons, which are to say systems that are in orbit that we believe are designed to potentially attack our systems in the future. And perhaps the one that is that people may have heard about most recently involves the potential deployment of a nuclear system in orbit, a nuclear weapon system in orbit by Russia. So all of those present critical challenges to the Department of Defense and the nation as a whole, as well as to our allies, to ensure that we develop systems that are resilient, that can deter action, but if action can't be deterred, that we are in a position to prevail in case our systems are in fact threatened and attacked. So let me stop there and just turn it back over to you to see if there are any questions.
Yeah, thank you, Dr. Dorland. So maybe building on that, and we can then circle back to see if we have any audience-related questions on that topic. I want to turn it over and maybe get a little bit of the industry perspective here. So Diana, what role does Lockheed Martin's IGNITE program play here in designing resilient systems for space? And maybe related, how do you prioritize resiliency in the face of this growing reliance on our space assets?
That's a great question, thank you. So I think as we all just heard, resilience is becoming increasingly important. And traditionally in space, we've thought of resiliency as point-to-point. So taking the example of a GPS system, if someone is jamming GPS, we can increase signal power, and you see us doing that on our modern GPS 3F satellites. If someone is spoofing a GPS system on the end node, the receiving node, we can add authentication or other means. We're beefing up point-to-point. But the shift to how critical space has become as infrastructure is leading us at IGNITE to really think about it as resilience at a holistic level. If you think about something as familiar as driving a car down the road, if you get in an accident, you can pull over to the shoulder. You can go down the surface road. If the traffic light goes down, everyone knows, take a turn like a stop sign. And if somebody crashes their car and can't drive it and gets hurt, emergency vehicles come with lights and sirens flashing. Everybody gets out of the way. They'll take you to the hospital. And so that's resilience. That's resilience through excess capacity. That's resilience through CONOP. And that's resilience through prioritization. And all those aspects now have to be thought of in terms of our space infrastructure. So that's really where we're focusing a lot of effort today in terms of we have a stack of tasking that needs to be done. We have a lot of dissimilar nodes up in space that could potentially run that task. So how do we autonomously deploy those tasks to those edge nodes? And then via prioritization, via monitoring the health of those nodes, autonomously redirect tasking so that we get the information we need, we get the tasking we need as robustly as possible, distribute against all those nodes, knowing some of them will go down either inadvertently or on purpose. And so that's really a critical focus area for us right now.
Okay, yes, so very much this topic of moving away from the nodes and really thinking about all of that more holistic look at this and the interplay there. So Kristin, now given Aerojet Rocketdyne's propulsion expertise, how do you see advancements in the propulsion systems now increasing this need for resiliency in our critical space infrastructure?
Yeah, well, thanks, and great discussion. Thanks for letting us be here today. When I think about the need for resiliency, we need to replenish and restore lost capabilities, have that ability to do that, but also we think about distributing more of that critical functionality across many satellites. So we're seeing a lot more in the proliferated constellations, and that's not just about constellations in LEO, but really truly making more proliferated constellations across LEO, MEO, GEO, mixing low-cost, medium-cost, exquisite systems, and really trying to get that more proliferation out. When we see that, we're seeing a lot more need for shorter duration thrusters, a lot of times more inexpensive thrusters, being able to produce more in larger quantities at mass, high delta V in small mass quantities, being able to move very quickly. Because we talk a lot about when we see resiliency, it's resiliency through maneuverability. And how do we be able to maneuver, whether it's across from orbit to orbit, in chaotic orbits, proactively, offensively, defensively, needing to be able to have more maneuverability through space, and then the propulsion elements that come with that. So we're looking at a mixture of whether it's chemical, electric, nuclear propulsion. There's a lot of needs and combination of needs to be able to have that resiliency in space. And actually, and also when we think about very low Earth orbit and VLEO, the air breathing systems that kind of give us unlimited maneuverability because the air is constantly there, right? So a lot of changes. We talk about dynamic space operations and that need for maneuverability. What we're doing, I already mentioned, we work through chemical propulsion and looking at more high-performing propellants, options for refueling, higher power, higher ISP electric systems, looking at our upper stage engines with longer duration, being able to have multi-restarts, and just recognizing that space is now a lot more congested and contested, and the maneuverability that's going to be required as part of that.
Great, very good. So certainly a lot here about maneuverability, and really in the operation space, I think that's really also where we're going to be challenged as we think about space as a critical infrastructure. So let me just see if we have an audience-related question in this area of space as a critical infrastructure. Otherwise, I will move on to space exploration technologies. Let's see. We have a few questions, but I don't see any in particular related to the space as a critical infrastructure. So we will circle back to some of these when we do more of the general questions. Okay, so let's talk a little bit about our space exploration technologies. Certainly, if you look now at some of our lunar missions, such as Artemis, that is laying the groundwork for future Mars exploration, I think we can think about how some of our exploration architectures are evolving and how there's some differences in the infrastructure that are going to allow for greater mission success. And so when you think about, as well, space technologies, there's a number of the advanced ones here that are starting to drive our current lunar missions and the future lunar missions, and then laying the groundwork for Mars. Some of these might be advanced propulsion systems, we've talked some about that, robotic systems and rovers and habitats, navigation and landing, radiation protection. So there's a pretty large number of technologies that actually need to be enhanced here and developed to be able to support this lunar and Mars exploration. So why don't we talk a little bit about some of those technologies themselves. So I'm going to start here with Kristin, and think about a little bit more towards sustainability. Of course, now when we think of power sources, everything is about bringing, your power sources from the individual mission standpoint. So with NASA's Artemis campaign now aiming for sustainable lunar presence, what are some of the key power challenges now for surface operations?
Yeah, well, first I just want to say how exciting it is to be part of the Artemis team and the Artemis generation and the exploration we're going to do with that, and getting humans back on the moon's surface after quite so many decades. And it's just thrilled to be part of that, of the Artemis generation. So we're getting ready as an update, if you're not tracking it as closely, we are preparing to launch the second Artemis, second space launch system rocket in 2026, and then land humans and astronauts back on the moon in 2027. So really excited about what that is to come. It's proven, it's flown once already, so it's the most powerful rocket in the world right now, and the only rocket that can take us into that cislunar orbit. So really excited for that future. But back to the power part of that, give my little plug. We are looking at sustained lunar operations, right, and having a sustained presence on the moon, and that's going to teach us a lot. So eventually, NASA talks about a moon to Mars, right? Eventually getting to Mars, but we need to learn on the moon first. And the moon's a pretty harsh environment. Temperatures can range from 260 degrees Fahrenheit on the warm side down to 280 degrees negative Fahrenheit on the cold day. So really extreme temperatures. That's going to have issues for humans and for machines and robots and other technology there. You'll hear a lot about survive the night. A lunar night is 14 Earth days, so that's 14 days of no solar. So that's where power is going to come into play, and where we really need to start focusing, and where we are focusing on more of the nuclear power generation and nuclear power sources to be able to get a lot of power for sustained periods in small packages as well. So, and power is needed for everything, right? It's needing to keep the astronauts warm or cool for any of their energy sources, for mobility on rovers. Everything's going to need power. And what NASA recently has baselined as part of the Moon to Mars architecture, fission surface power, for what they want to use on Mars. So that's going to make it really help us with what we're working on, FSP for the Moon. And there's a number of projects underway right now, and contracts underway. We're partnered with Westinghouse as part of that. But really leveraging technology that's already been out there, nuclear power technology, like our multi-mode RTGs and our next-gen RTGs that are powering things on Mars and on the outer planetary systems, and using that expertise to look more on the nuclear side to be mass competitive with that.
No, thank you. And maybe I'll look at this. You certainly mentioned nuclear power as being sort of the big place where you're really looking. There is a question that has come up kind of mentioning on the three, types of propulsion, the chemical, nuclear, and electric, and where we think that might be heading. And certainly, I think, or what propulsion would be most prevalent, and you certainly spoke to nuclear. I don't know if you want to take on the second part of that at all.
Well, again, it's all of it. We need some of the chemical propulsion on thrusters to get us out into deeper space. The electric propulsion, we're working today, the Advanced Electric Propulsion System, which is a high-powered 12.5 kilowatt system for the Lunar Gateway, which will be the kind of a space station circling the moon, orbiting the moon. There's going to need to be nuclear propulsion, nuclear power as well. So it really is a combination of solutions that's going to be needed across the board.
Right, yes. Okay, very good. So let me turn over then to Diana here, and ask about with the Ignite focused on rapid innovation, how does Lockheed Martin address the challenges of creating an exploration architecture that balances both scalability and adaptability for some of the longer term goals that are needed for Mars?
Yeah, and I have to say, I've only been here since this morning, but the energy around going to the moon and going to Mars is absolutely incredible. I think it's the one thing we're all really excited to go tackle next. And it's actually one of the most fun things we get to do is imagine a day in the life. And so that's really where we always start is days in the life on the moon or days in the life on Mars. We're going to wake up and we're going to eat breakfast and we're going to go out and do some experimentation. Maybe we'll go mining, all the way down to what are we going to talk about at dinner? There's no weather. So what do you talk about if you can't talk about the weather? And we really imagine our lives in these scenarios. And once you get through that, you start to be able to distill the core things you've got to do, the core technologies. And from there, we really start to then get into implementation. NASA's got a fantastic architecture and a series of technology gaps, and where we're really living now is imagining implementations. So how can we make all these things really happen? And so I think we talked a little bit about power. So for power, we can imagine where you'd want to have multiple different power sources. So how do you build a power depot that's flexible enough to handle hydrogen and methane, because we would want one maybe more for the moon and maybe one for Mars, and how do you make that happen? Our space infrastructure is likely to build slowly over time, so you want it to be modular. How can I build up and keep this affordable so we can keep progress going? And so that's really where we're focused now, where are the core building blocks, things like soft goods, so inflatables. We've done some pressure lock testing there where we can have very low volume, low mass structure that we can then use in orbit or on the surface of the moon or Mars for a variety of applications. And so it's just imagining the building blocks and then starting to prove them out on the ground. And I'm really excited by some of the progress that's already been made to date and excited to see where we're going.
Great. Yeah, very exciting stuff to see where we're going, a lot of developments here in this propulsion area. So I'm going to turn it over, maybe get the government perspective here, Dr. Dorland. So maybe you can talk a little bit about what do you see the DoD-sponsored research play for enabling deep space exploration, and perhaps maybe talk a little bit about any synergies between some of the defense needs and then NASA's exploration goals.
Sure. Just want to, of course, point out that the DoD has been involved since the start in many respects with going to the moon, as a support activity to NASA. For example, I'm sure everybody's familiar with the fact that the original Mercury astronauts were military officers. Neil Armstrong was a civilian military test pilot, and so forth. But beyond that, we've done a lot of technology development very early on. A good example is the Centaur upper stage was developed by DoD and DARPA, and eventually became something that NASA has utilized. I'll mention too that you talked about working together within across departments within the government, and I just like to salute the leadership of the Office of Science Technology Policy at the White House, who over the last few years they led a study, an interagency study, to put together the the National Cislunar S&T Strategy, Science and Technology Strategy, which is available online. I'd recommend reading that for anybody interested in the science and technology that we think we're going to need, going to the moon and beyond. And also, they've been working on an implementation plan with us, and a lot of that, as part of that, we've within the government, we've worked together to try to figure out, who has leadership in these particular lines of effort and who plays a support role. So, obviously, for going to the moon and going beyond, the DoD's role is primarily in support. I'll give you a perfect example of one of these synergies. It's trying to work through how we, as a government, working with our Artemis allies, will implement PNT at the moon in the cislunar volume. So that's a big challenge. The very first challenge is that we had to deal with is that clocks on the Earth don't tick at the same rate as clocks on the moon, and clocks on the moon don't tick at the same rate as clocks in the Earth-Moon Lagrange points, right? So those are some of the issues that we've been working through right now. DoD led the development of and operates GPS, which is the primary source of PNT, including timing, but also navigation and position information around the Earth. But we're looking at the moon. We're looking really about how DoD would work with an organization like NASA, who would lead the development as part of the overall activities out there, to lead the development to be able to deploy PNT systems at the moon to support operations on the lunar surface and also in the vicinity of the moon. So I think that's a perfect example of some of the partnerships and some of the teamwork that we've been doing. Because DoD really has the expertise in things like timescales, and now we're trying to work with NASA to transfer that information and transfer that expertise to NASA. The last thing I'll mention, and you asked about some of DoD's particular expertise for the moon. Give you another example. Department of Commerce is going to have the space traffic management lead for cislunar. Obviously, somebody has to keep track of all the things that, looking forward in the future, all the thing, all the various probes and satellites and missions to the surface and so forth, to ensure safety of navigation out there. That's going to be Department of Commerce's primary role. But obviously, DoD has plenty of expertise with sensors and so forth. So we'll be supporting Department of Commerce in that. The last thing I'll mention too is I'll just mention that DARPA has really led the way in some of these areas, and they recently completed what they call the Luna 10 study, and the Luna 10 is fascinating. DARPA is looking at the moon, and they basically asked a very simple question: what would it take to develop the civil infrastructure to support a commercial activities, the infrastructure on the surface of the moon to support commercial activities on the moon. So I've been part of the development of that, and so I would just suggest that people keep their eyes out for that, because this year they're going to release their report, and it's a fascinating report. It's primarily contributions from commerce and industry, ideas about how to do things like what sort of power, how would we distribute power on the moon, how would we distribute communications, that sort of thing, all to support a future lunar economy. So I think that sort of covers in general, where we are with this. We're very interested in the development of new technologies to support getting to the moon and beyond. But our primary role right now is really to support the other government leads in these areas.
Yeah, thank you. I think really interesting here, sort of the interconnectivity here, as you mentioned, and again, towards that sustained lunar economy you mentioned. So I wanted to maybe just circle back here just with Kristin and Diana a little more on these advanced propulsion systems before we pivot to sort of innovation more broadly. We've certainly seen that in-space propulsion, orbital refueling, space depots are transforming the logistics and the economies of space operations. And there was a mention already about space depots that they could really serve as the enablers for sustained lunar and Martian exploration, and helping here design to be able to facilitate the storage and production of any kind of resource, whether that's fuel or water and oxygen. So I do want to maybe circle back here and just go a little deeper in some of this propulsion area with the panelists here, and then we'll pivot. So maybe just, Diana, back over to you. You mentioned the space depots. Can you talk a little bit more about how Lockheed is using or exploring the use of space depots to be able to kind of support the long-term sustainment, and what are those challenges involved there?
Yeah. I think space depots feature in every one of the future sustained exploration architectures. I think at some point you hit the tipping point where it's economically infeasible to start lifting all those things out of Earth gravity, and you move on to depots, be they in LEO orbit, be they in cislunar orbit, or be they even on the surface of the moon. We will need caches to be able to sustain a rapid cadence of exploration. Some of the key challenges there, I think one of the big ones that we're currently tackling head on is the cryocooling. So being able to maintain temperature, avoid boil off, because if you ever look at the amount, I think it's something like even cooled, you can lose up to 4% a month of your fuel storage. So unless you're planning to be just in time to every fuel delivery, if you want long-term fuel storage, you're going to have a very good cryocooling system. We have a lot of experience with cryocoolers for different applications, but nothing at the scale that's going to be required. So I think that's a very cool technical challenge we've got to hit. But longer term for the depot architecture, I think the biggest challenge is actually economic. So do we think we're going to hit a cadence of space exploration that will actually make this economically viable? Will there be enough of an incentive in terms of profit for commercial companies to want to massively invest in a space infrastructure that allows for a depot structure to hit, a trip to Mars maybe every 26 months or so? I think that's going to be a big hurdle for us to hop over. I think the technical challenges are all very solvable, but I think the biggest barrier to entry in terms of a depot-centric architecture or even sustained lunar or Mars development in general will definitely be the economic barrier.
Yeah, so economic and then cryocoolers at scale here. Yeah, they sound expensive, so.
They're very expensive.
Yes, very much so. So, and maybe one more for you, Kristin, here. Again, we are talking a lot more about expansion of operations. We've talked more about lunar, so we are talking about going well beyond the low Earth orbit world. So how do you see, again, you've talked some about that affecting propulsion, but maybe in the grander roadmap here, how do you see that affecting the propulsion?
Yeah, some of what I have said, the need for the multi-different propulsion sources, because we are going to need to have continued and increased in-space maneuverability, right? Whether it's for resiliency or even just to get things where we want them to go. Because we're, like you said, beyond LEO, there's going to be a lot more out in MEO and GEO and beyond. And I think one of the things we're seeing too is that there's not very many launchers that can get things as far as we're going to want to go. So there's going to be a much larger need for kind of in-space tugs and what the requirements will be for that. So I think a lot of that's still kind of in the infancy of being shaped of what those requirements might look like, what those missions might look like. And I think when we think about it too, it's, back to what Diana was saying, is in terms of the economic hurdle of it, it's really understanding and trying to get a good handle on what is that mission going to look like, being able to partner with those that are doing it and understanding that so that then we can be innovative in terms of developing what the right solutions are. And I think there's still a lot of development and understanding what those missions may be, whether it's on the kind of commercial side, whether it's military side, it goes across that need of really trying to understand what those missions might look like, how do we do that, because this is, a lot of what we're doing is long cycle development and not very quick, so we're projecting pretty far out into the future. We want it to be more quickly, but it's trying to balance how quickly can we innovate, but what are those real needs, and then what's the kind of economic benefit of being able to do that too. So we're investing and putting our resources in the place to do that.
Yeah. Okay. Yes. So very much a delicate dance here. All right, so let's talk. We have a lot of questions coming in, and we will definitely have time here for that. I want to cover a few more areas, and then we'll definitely allow time here. I see questions coming in kind of across the gamut of things that we've been talking about, and then in some areas that we haven't yet quite touched upon. So let's talk in the broader area of innovation here. We talked already about transitioning, moving away from sort of single point assets to large interconnected networks. And that has implications in terms of the way you think about architectures and how, as well, you actually design and then test and then operate, very much so. So I think all of this has caused a call for more novel approaches as we think about these systems. So a lot of things are driving that, or needs for thinking about things some differently. And so I guess maybe I'll turn to Dr. Dorland first. How is your office fostering innovation in system architecture and or any other parts of that life cycle beyond architecture to ensure mission success in contested environments?
So we work very, very closely with Space Force and Space Command and other components of the department that develop and transition these types of systems. So we're at the early stages, the 6.2 stages, and part of our job is to move stuff from 6.2 through the various valleys of death all the way to operations and deployment. So part of what we do is we work very closely with those other components and within the department to ensure that these systems are going to meet what we believe to be our future needs. So these systems operate together. They're resilient, and they're going to be effective. I will say that one of the things that we're looking at very closely right now, just looking out in the future, we don't worry so much about what's going to happen tomorrow or next year. That's more Spacecom and Space Force's roles. So we get to maybe look a little further out and ask the question, what are we going to need in 5 or 10 years? And we talk a lot about resilient systems. I'm not sure if you're familiar with the work of Taleb and the Black Swan, the author of the Black Swan. He talks about something called anti-fragility. And anti-fragility, if you think about resilient systems as systems that sort of can take a punch and can continue to operate. Maybe they're degraded, but they can continue to operate. That's sort of where our big push is now. But beyond that, there's this concept of anti-fragile systems, and that's systems that actually get stronger when they're exposed to stressors, right? And a perfect example of this is our biological systems, like bacteria. If you expose it to an antibiotic, you might kill 90% of the bacteria, but that 10% that is left is then resistant to that antibiotic, right? So one of the things that we're looking at is, what is it going to take, as we become more resilient, what is it going to take to go to that next level? What is it going to take to start building anti-fragile systems that will actually improve upon being exposed to stressors? And one of the things I think we're thinking very, very carefully about is, the question is, does that require the development of AI systems? So, we talk about 5 or 10 years in the future, we talk about these systems, exposing them to stressors. Do these systems then have to somehow learn how to overcome these these sources of stress to them, and then they become more powerful, more effective after that? So I think if you're talking about sort of longer term, I think a lot of what we think is the most interest and potentially the most useful to us in terms of our capabilities is probably along the lines of AI and actually getting autonomous, not automated, but actually autonomous systems up into orbit, and then ensuring that they can respond to threats in a sort of more than resilient way to these sorts of things. So does that answer your question?
Yes, and I think no panel would be complete if we're going to talk about new technologies and importance in space applications if we didn't talk about AI. So, and I think the way you've kind of captured that in terms of beyond the resiliency with the anti-fragile systems is a pretty interesting area for discussion here. So yes, let me now turn here to our other panelists here, and I'll see if there's any question. Well, I'll turn to the panelists here, and then I'll tee up maybe some questions if we've got them. So Diana, maybe over to you. What role does Ignite play in driving innovation for interconnected systems, and what lessons are you learning from that as you set that up that could be applied to the broader space ecosystem?
So it sounds very obvious, but making things work together that originally weren't intended to is actually a very hard problem. That sounds very obvious, but that's a lot of what we do at Lockheed Martin. We're an end-to-end integrator, and so we spend a lot of time with the classic Apollo 13 concept, right? You got to make the hole this fit into the hole for that using nothing but this. With that, you can do it. It's painful, it's inefficient, and your solution is not very robust, right? It's a plastic bag and duct tape. And so designing systems from the beginning to work together, that is really the key that, that unlocks the future of a joint sustained space exploration campaign and a joint space economy. And all that comes back to standards, and that might sound a little bit boring, but we spend a lot of time engaging with industry, engaging with our governments, engaging with academia to understand the broad swath of use cases and help implement and drive forward new standards for space and space exploration. If you think back to a terrestrial example, standardized shipping containers unlocked a global shipping economy because all of a sudden everybody could fit on the same boats and use the same crane and use the same railroad and use the same trucks. What is the equivalent for space? How do we get to that enough standardization in terms of our interfaces that we can all work together to be incredibly efficient and really take that next leapfrog forward while maintaining our uniqueness, our contents, of those containers specifically. So that's one big area we're focused on is helping to drive forward that standards. The other lesson, I don't know if it's a lesson, maybe a lesson we haven't learned yet, but we're about to, is the incredible importance of cybersecurity in space. So space has always been somewhat of a high ground for cyber for a variety of reasons, and that is definitely no longer the case. And so we're seeing an increasing emphasis, both from a policy position, from a threat environment position, and from just we know is coming. And we need to build cyber resilience into our systems from the ground up, because the more connected you are, the larger your attack surface is, and you can worry about things like folks walking up from a less protected, less vital system all the way up to a more protected, more vital system. And what are the consequences? We talked about space as critical infrastructure. Can you imagine a cyber attack that took out all of Starlink, that took out all of, AHF? And so it's a really scary proposition, and an area we all really need to be focusing on is how do we start mandating that and building that in from the ground up, because the more interconnected you are, the more you are dependent on everyone else.
Thank you. So Kristin, what does L3 Harris see as the hurdles to innovation?
We've certainly talked about some of them, and I'll just go back to really trying to understand some of the requirements and partnering with our, the end customers, whether again on the commercial side or on the military and defense side of the business, to understand what those mission requirements are going to look like to allow us then to come up with the solutions, and not avoiding their urgency or the tendency to want to overprescribe a technical requirement. Certainly there are technical requirements that need to have it, really thinking more about mission requirements and allowing us and the larger us to come up with the innovative solutions. The other thing I'll hit on, I mentioned before, but it's actually policy sometimes can be one of the bigger hurdles, not just the technology piece. From a whether it's NASA or and any of the government side of the business, NASA or military, the government funding is not as consistent as we would always like it to be. And as I mentioned, there's a lot of long cycle development, so having some trying to get more consistency in funding and understanding where that future goes without the disruption, so that we can plan, we can develop, we can deploy solutions, and understanding what the priorities are, though. So it's a lot of times we can do the rocket science, but we need the funding streams to come through. I will just give a shout out to NASA's STMD, the Space Technology Mission Directorate. So they rolled out earlier this year and over the summer, actually getting input from all of industry and all stakeholders about kind of what are the top technology shortfalls and technology gaps. That was really valuable, because we all got to have a say in it. They were able to kind of rack and stack, and now we have a clear understanding of what the priorities are in terms of needs, where there's gaps. We understand that that's where they're going to kind of prioritize funding to address those top level shortfalls. survive the night is right up at the top. I mentioned that earlier. How do we survive a lunar night and not having access to solar power? So, I think that's a great example of something NASA did recently to try to help get the inputs and really get us all kind of aligned on where the priorities are going to stay. So even if maybe funding may be inconsistent from time to time, at least we know kind of there's clear priorities and we can stay focused on where our efforts are.
Great. All right, so good. So I think we will maybe pivot to one other area we want to kind of go a deep dive into, and then we'll pick up some time for a number of the audience questions that have come in. So I want to cover a little bit in the area of autonomy and robotics. Certainly we've seen advances in autonomy and robotics, and those are really shifting, I think, the way we think about space operations and surface exploration, and then even the efficiencies of multi-agent systems. So much there, I think, happening in the autonomy and robotics front. So maybe, again, starting here with Kristin, how do you see the role of autonomy playing and supporting the next generation of propulsion and power systems?
Yeah, I think autonomy and AI is going to continue to have a large role in growing. There's so many assets. We talked about space being very congested. Now there's so many assets that we can't keep humans in the loop on all of it. And we're going to need systems in space, satellites and whatnot, to have more onboard processing, more autonomy, so that spacecraft and space vehicles can self-determine if they need to reorient it or maneuver, avoiding collisions, avoiding hostile actions, and being able to do more of that onboard processing, because humans aren't going to be able to stay in the loop, not going to be able to do it at the speed we need it to be done. We need to think about the risk of, we were talking about cyber risk, adversaries taking out our ground data links. If there's not an ability for us on the ground to be able to communicate up with satellites, another reason there needs to be more onboard processing and autonomy decisions there. And then with that congestion, satellites being able to have intercommunications and being able to talk with each other, say, hey, I'm moving this way. Okay, that means I'll go this way, kind of turn signals almost for space, and in some kind of way to have some of that, be able to have that cross-system communication. I think the standards is a good part of that. How is that going to work if we're each making different satellites? Can we use some kind of common standard of how that communication may be? But I think we're going to see that, because we're just going to need AI. The decisions are going to have to be made faster, fractions of the time that a human could do it, and there's just not going to be the capacity for humans to stay in that loop. So I think it's going to continue to be outsized importance as we go forward.
Yeah, absolutely. How about you, Diana? How do you see Ignite prioritizing the integration of robotics and autonomy there for, space ops and for your tech development?
Kind of as Kristin said, I think it's absolutely critical today, and I think the importance will only increase, both in terms of the complexity of what's being asked to be done. We sometimes the human brain just can't keep up with the level of complexity. And then as you move into more of an exploration phase, a human is an expensive resource. It takes an incredible amount to keep a human alive in space or in the moon or in Mars. And so there'll always be a human being will always be a very limited resource to a mission in terms of what we can allow them to do, right? They're relative, we need them, but they're expensive to have in terms of the resources it takes. In some cases, they're limited in terms of decision making or strength or ability to survive in the environment, and they're very vulnerable, right? If space chutes puncture or airlock leaks, they're gone. And so we're really going to have to prioritize what we have humans do versus what we have the machines do. And the more we can have the machines do, the less resources we'll have to spend on a large crew, and that's going to be really important. And so if you look forward, I see assistant rovers next to the human lander going off to do the dangerous operations in the dark areas of the moon we don't want to send a human to, because we don't think they're not going to survive the night, or that's very risky. Or maybe it extends our reach. So if we have a base camp on Mars, maybe we send an autonomous probe out to one of the moons. We've already seen a lot of exploration with autonomy and robotics. We recently did the sample return from the asteroid, where they flew out, scooped dust up, and brought it back. We are years away from having a human be able to do that, and that was really cool. And so I think it is going to be a critical part. as Dr. Dorland said, I'm interested to see where we had the move from autonomy to AI. So Lockheed recently stood up a subsidiary called Astros AI, and they're really focused on trusted AI. And that's going to be an important development for us. So anybody who's ever gotten a really garbage answer from ChatGPT, you can imagine why we don't want ChatGPT running our human critical systems or even mission critical systems. And so getting AI to a point where we can trust it, to the point where we understand its decision making and where we'll let it run systems that are keeping people alive, keeping critical infrastructure running, that's an area we're really focusing on because we need that level of trust, that level of reliability in order to be able to turn over the controls.
Yeah, thank you. I certainly resonate with that. That's certainly part. Getting to that trusted AI is a big part of the investments that we are making at Aerospace too, with our AI strategy. So Dr. Dorland, maybe how do you see DoD investing now in autonomy to improve operational efficiency and safety in space ops?
Yeah, that's a great question. I'll note that that we've already seen other nations doing things in orbit involving robotic arms and so forth, like with the Chinese, for example, with their SJ-21, demonstrating the ability to utilize it at GEO. And I'll just mention that we, I think we all view that as a critical capability in the future that we want to develop. And one of the activities that's going on right now in DoD is the DARPA RSGS program. So DARPA is actually working. They recently took delivery from NRF, from the Naval Research Lab, of this system, and the goal is to put this system into geo orbit and to demonstrate our ability to do these sorts of operations. So looking forward to the continued development of that mission. Obviously, if we talk about the sheer volume of systems that are going to be up, we talk also, as mentioned earlier, about how valuable humans are. Not just sort of intrinsically, but also there's just a huge cost associated with putting a person into orbit and moving them around in orbit. There's going to be, the future, we see the future in many respects as being systems, these on-orbit systems that are designed specifically to be able to refuel and potentially repair other systems, whether they're DoD systems or commercial systems, be able to do that on orbit. We see that as critical, and it seems unreasonable to have to put people there, to have these as manned missions. So this is another aspect of AI that we see develop. Autonomy, I should say. In this case, we're talking, I think, primarily about autonomy. That we see a critical role for autonomy in the future. I'll mention too that, real quick, I'll mention that we're looking forward to seeing a potential demonstration of this sort of orbital refueling capability in the not too distant future with Starship. So that seems very, very promising. If they can demonstrate the ability to get a Starship in orbit and then refuel it in orbit, I think that'll be an amazing first step towards what we're talking about now. I'll mention too that as we talk about going beyond GEO, we start to and the ability of humans to control these actions, we start to, in some respects, run into some fundamental limitations associated with physics, right? So the moon is. The round trip light travel time to the moon is 2.6 seconds. We're talking about Mars, it can be up to 45 minutes. So we can't have people doing things on Earth or in Earth orbit effectively, if at the moon or certainly at Mars. So we have to be able to develop these capabilities to these sorts of repair and refueling and all of these capabilities are really going to have to be autonomously developed and deployed in situ. These capabilities are going to have to be in situ capabilities. So I think that's sort of the way we see this. So we're tracking that other nations are doing this. We're doing this. DoD is doing this in the form of DARPA leading this activity. And we're looking forward to seeing the development of this capability just going forward from here.
Great, no, thank you. So, so we've talked certainly a lot about here space as a critical infrastructure, a lot about some of these enabling technologies, some of the themes in innovation, autonomy, robotics, AI. So we have some questions here that have been teed up, and so we will allow for a few of those. And I think one that's interesting, maybe a little bit adjacent, but certainly important given we've talked about so many areas where we need to keep developing. And there was a question that says, what are the best ways to prioritize some of these R&D investments to fit within limited resources? So I think that might be an interesting one to take and get the government and industry perspectives, and certainly I can offer FFRDC perspective there too. So why don't we take that one, and then we'll take a few more as we go here. So in either of you want to kind of offer up a little bit about, given we've talked about so many very challenging technologies, what are some of the ways that we think about prioritizing them? Anything that you guys do in your portfolio?
So this is a topic of endless debate.
Yes, it certainly is.
And I think we've settled on a few. So first of all, there's what I call the table stakes. There's some foundational areas, things we know we're going to need. We're going to need power. We're going to need propulsion. We're going to need avionics. Like there's certain things humans support systems. Like there's some things you got to bring to the table, and then there are the things that we think are leapfrog technologies. And then we have to carefully pick the mission areas, because we don't just address space at Lockheed. We address a full gamut of applications across military, civilian, NASA. And so really, what are the core game-changing technologies that we think only we can do? And then where can we partner or have someone bring someone else along with some great expertise that can do something as well? But I think in an era of limited resources, you do have to pick and choose, and sometimes that's based on an economic incentive. And sometimes it's just investing early in what we consider the leapfrog. So what are the next leapfrogs? I don't think AI is a leapfrog anymore. I think it's here. So what's the next big thing where we need to start investing now, so we won't have to invest a lot later? And so there's not really a great formula. We actually have formulas. We have different one, I think, every year. But I think that we do what does everybody need? We'll do those, and then whatever's left over, we'll do our best to we'll place our bets on what we think is going to be the next game changers.
Yeah, and I'd say we're very similar approaches. There's way more things we'd like to be able to fund and invest in than we have the funds to be able to do so. And so in addition to what Diana said, it's also, again, back to what's the needs that we see our customers, end users, those ultimate missions. What are they? Where do we think we play a unique role into that? What feedback are we getting from them? That's where the ability to be able to partner more and really understand where things are going from a end use need is what helps kind of help us decide on kind of what makes a cut and what doesn't in any particular year. But otherwise, it is very similar. There's things we just have to go do and to continue to evolve the technology. And then there's those groundbreaking things we're trying to invest in.
Yeah, no, I think similarly, and thinking again, you think about it as a portfolio, and as you said, some things are more evolutionary. What are those things that need to be invested in that could be leapfrogging or game-changing? But I think also sort of allowing, some amount of investment for things that come in from, I'll say, the principal investigators versus some of the things that we know are more of a top-down directed, if you will. So sort of allowing for all of those kinds of things into a portfolio. Dr. Dorland, anything you want to add on that one?
Sure. Yeah, I think it's important to when we talk about different sort of types of development activities. Most of the development is just normal evolutionary development, and that's sort of the core of what we do. A lot of that comes from commercial industry, and that we just sort of count on that being there. It's sort of the Moore's law of progress. If you just wait long enough, you'll have a better computer, right? I'd actually say that there are two types of sort of more accelerated developments that we also keep track of, and I think that these are where we given limited resources, these are where we try to perhaps focus some of our or most of our attention. And the first is what I'll call step function developments. And these are areas that are evolutionary. They're not disruptive, but they represent significant increases in capabilities. And the other ones, which I mentioned earlier, are what are sometimes referred to as black swan events, and these are highly disruptive. I mean, I'll give an example of a black swan disruptive technology. You might think of Netflix, for example, and streaming, right? So 20 years ago, everybody went to, or 25 years ago, whatever it was, everybody went to Blockbuster, and those are just, I think there's one Blockbuster left, and I think it's in Alaska. I don't know why, but the development of Netflix and the ability to stream just completely disrupted that industry. So we have to be this is sort of a double-sided coin for us. We have to be wary. We have to make sure that we don't get Netflixed, if you will, by somebody else. But we also have to make sure that we can try to spot those very disruptive technological advances for us, and we can pounce on those when necessary. I'll mention too that it's sort of a different aspect of prioritization. From our perspective within the department, we have to be careful, because a lot of the stuff we've talked about here involves sort of NASA's equities, or some other organization, some other agency in the government. So we can't spend Department of Defense resources to support what is clearly a NASA area, to develop what is clearly capabilities that NASA needs. Now we can, insofar as they also cover things that are interesting to us, we can work with NASA. What we really have to focus on for the department's resources, we really have to ask the question, how does that help us defend the nation? How does that help us deter conflict in the future? Or if deterrence is not, doesn't work, how does that help us prevail? So those are really, when we look at prioritization of resources, those are sort of the things that we really look at. We have to focus the department's resources on the department's mission, and that, I'm sure it's the exact same way in NASA and at NOAA and other organizations. So. Back to you.
Okay, great. So I think we've got a lot of different questions here. Definitely won't be able to tackle them all, but let me pick one here. This one's one we've certainly all heard. Let's see. Okay, so programs I have worked on over the years appear at either extreme: over testing and endless risk mitigation and not flying for years, or never in driving up costs, or smaller commercial companies that act as if the Wild West and result in minor to major failures. How can we get to a happy medium? So, anyone on the industry side want to start with that one?
So this is something we've been working on for the past couple of years, actually, and I think the SDA programs were a good impetus for those. If you're familiar with the various tranches from the SDA, the Space Development Agency, because they really pressed at least us to think about the problem differently. And I think we have seen two extremes. We have seen the traditional, for those familiar with the nomenclature, Class A programs, and then we have seen kind of the Wild West where nothing really works. And the optimum's always somewhere in the middle, at least for some systems. And so our struggle has been, we actually do have some systems that have to work. We have to keep that mindset. If a GPS satellite doesn't work, people get very unhappy. Yeah. But we do have to have that faster gear, and it's not just, we just don't have the time anymore. And sometimes an 80% solution today is better than a 100% solution in a week. And so I think it's what I call risk intelligence, understanding the risk you're taking. And we've demonstrated to ourselves a few times that this does work. We've had a couple of different demonstrations out of the Ignite program where we purposely set up to go as fast as we could and let the teams just rip on making decisions, and then use that to inform our mainline programs. And so you can look at the curve. We do a lot. You can look at statistical analysis of where defects happen to compare back your test profiles. You can do a lot of different things. I think the refrain I do hear a lot is people are nervous about it. People who are used to having to guarantee success are very nervous about that. And so some of this is almost a psychological exercise, because I need to unlock the expertise within the team, because they're the ones who know, what was that, where the curve bends and where it breaks. And so giving people the psychological safety has been at least 50% of the problem in terms of being able to go much more quickly. And so we've done everything from bringing in folks with different backgrounds to pair up to actually writing down program directives to say, you're allowed to run with scissors. So we're trying a couple different things.
Anything you want to add on that?
I think well covered. I think one thing too is that we're seeing that, as the some of our very experienced workforce is choosing to retire and whatnot, and less experienced folks coming in. We're seeing a shift in just experience level, and so a lot of the comfort in terms of understanding, okay, this is going to be good, comes from years and years of experience. You don't get that overnight, and so that's what we're also kind of balancing is, like I think you said, kind of how do we get some of that experience level over, partnered up and paired up, and knowledge transfer happening, things, because it's I think we've all been trained, especially we do a lot with human spaceflight, like there is no room for error, like it has to work, and we have to be 100% confident every time. But how do we make sure we're not over designing? And it's definitely a fine line.
Anything on this one, Dr. Dorland, that you liked?
Yeah, no, I agree with everything everybody said. And clearly with human spaceflight, we have to be very careful, and we have to accept only the absolute minimal risk. And similar with other types of some types of national missions, that's the same sort of thing. I would say that that I think that we need to figure out a way to be more risk tolerant. Because ideally what that does is that lowers the cost of any one mission, and we can get more missions for the same amount of money as long as we can develop capabilities that we need. I think we run the danger right now. We sort of, and I think everybody's alluding to this, we run the danger of locking ourselves into a very small number of missions where we've leveraged a lot of resources and so forth. And I think we all, if you've been involved in this area for any amount of time, we understand sort of how we got here, and we understand these sorts of decisions made sense at the time. But I think what we're seeing now is a lot of other countries that are trying to catch up to us are not taking the same approach. They seem to be, sort of throwing everything up against the wall and seeing what's going to stick. And so maybe if we could, and I think that's the way we were back in the 60s, certainly, and in the 70s. And maybe if we could recover some of that sort of mindset, that might be useful to us. I mean, we do have to maintain our national capabilities, but we also, I think we do need to perhaps be a little more aggressive and a little more risk tolerant in terms of developing new capabilities and looking at ways for efficiencies and so forth. And I really think recently, over the last 5 years, I think the commercial entities have really led the way in that area. So I think the government needs to take a look, and I think it is right now. I think the government needs to take a look at this and try to learn some lessons from some of these newer commercial entities.
Yeah, very good. So maybe just one more that we have time for very quickly here. There's a question about other kinds of R&D investments or other investments or work needed to improve the resiliency of our civil, commercial, and military space missions. And we talked about a number of the ways our systems were moving from the single assets, and a lot more in terms of building resiliency, in terms of ConOps and architectures and different things there. There are other areas or other places where we think that where we need R&D investments or additional investments here to get to that improved resiliency. Anything else?
One thing I'd added, I think relates, but really looking at the resiliency within our supply chain. Mm-hmm. We're a lot of these systems now, some of these larger proliferated constellations, it's larger quantities, and do we have a robust enough supply chain throughout the entire industrial base that's going to continue to support that? I think we've often been over the past many years driven to be much more lean, single sourcing, and then I know I'm living it right now. I'm sure we're all living it with kind of your eggs are kind of all in one basket with a specific supplier, a specific technology. And I think we really are seeing now we need to have much more diversity across the supply chain, multiple sources again, and that's going to give us ability to scale up, to move more quickly, get more competition across the supply base. But I think really ensuring that the entirety of the supply base is strong, and that we have the right skill sets, and that skill set's not just engineers, but the technicians, welders, all of the skills that are required to make the space industry base work. I think we have to really think through that too.
Yeah, very good. So I think one thing, I think we're kind of close to the end here. I wanted to do a quick lightning round with the panelists here to give everybody one more minute to just kind of close out here. You know, again, I think we've had a robust discussion. There's a lot of questions here that have come in and we haven't been able to take care of, but you may have time afterwards. I'd encourage you all to kind of reach out here to the panelists or myself for any follow-up. So let's see, before we wrap, one final question as part of our lightning round. I'm going to give you each a minute or so. In your view, what single strategic or technological development will have the greatest impact on the future space missions and the space ecosystem? And we'll start with you.
All right. So last month, all of Lockheed Martin Space E&T got together for our all-hands, and a gentleman named Joe Buck, who's one of our quantum subject matter experts, got up and said, "Good news, everybody. All the stuff I studied in college is now a reality. I could actually do it." And so he showed us a quantum imaging demonstration, and now and it was amazing. And at the end, he said, by the way, if you're not thinking about how quantum is going to change everything you do in all of your systems, you should be. And I was like, oh, shoot. Well, guess I'm going to have to go figure that out. And so I think quantum is that immersion technology that's almost to the point where we can start to use it in a practical manner, and it has the potential to foundationally change some of the constraints we're working with. So I'm just really excited to see where quantum takes us in terms of the space exploration and beyond.
Are you willing to share one of those applications?
Communications.
Yeah.
There's no point in going somewhere if you can't tell somebody when you get there.
Yes, very good.
Yeah. I'll take it from a not as technology point of view, but I think we're going to see a different construct. We're seeing it already with a lot of the commercialization of space, and I think there's going to continue to be a lot of change in terms of just how we go about creating, producing, developing, investing, and I don't think it's going to look quite like it is today with how the commercial industry is, but I think there's going to continue to be a lot more commercialization. I think there's just the industry is ripe for a shakeup of just how we flow requirements and get technology out faster.
Yeah, I mentioned this before. I think that, looking ahead 5, 10, 15 years in the future, I really think that the nation or nations that are able to develop and deploy AI systems and autonomous systems are going to have significant advantages over the ones that don't. So I think that's probably going to be, and quantum is probably going to be part of that. There's a lot that goes into that. But I'm just our world right now is moving towards these AI systems, and they're coming into play everywhere. My wife's a teacher. They're now incorporating it in teaching 12th grade English, and it's hard to say how fast. It's hard to believe how fast this is accelerating. It sort of came out of nowhere. I think people weren't expecting this a few years ago, and it's really developed a lot since it first, since ChatGPT first became available. So these sorts of things, I think, are really going to play a tremendous role in the future, and whoever has them first will have a significant advantage over the people that do not have these capabilities.
Right, and then your anti-fragile systems too, as well, right? Would be another.
Exactly. Yep. But no, it goes into a lot more than that. Not to use up everybody's time, but a really simple example is latency. I mean, if you've read that book, Kill Chain, the author there makes this point about anytime you have humans in the loop, things will take minutes or hours or days or months. You put a computer in a loop that can make decisions autonomously, it takes milliseconds to do that sort of thing. So those are the sort of huge leaps that this type of technology, in my opinion, that's the promise of it being able to deliver. So those are the sorts of things that are both promising and a little scary. So.
Yes. Well, very good. Well, I want to thank everybody for sticking with us and having some good questions here that have come in. Didn't get to tackle them all, but I think hopefully enjoyed the discussion here across the board from our panelists. And again, thank you for the time, and I would encourage you to reach out to us if you have any follow-up questions after the session. Thank you.
Thank you.